Hello, class. This is the first lecture that I've made in I think like 5 days because I've had my father break his hip, and yes, and he's going into a rehab hospital, which scares me even more. And then I've had 14 tons of gravel delivered, and I finished one driveway. So many, plus I'm closing on the 4-family next door to me in 2 days. So there's been so much going on besides doing lectures, and that's why you always want to get ahead, because you never you never know when a coronavirus pandemic or your father breaking his hip or something like that comes along. But what I did was I went back and I looked at the last lecture that we did, and I wanted to talk conceptually about the numbers that we got. I mean, everybody understands now, due to the derivations I've done with the telegrapher's equations and everything else, what really makes the propagation coefficient, right? And that is the attenuation coefficient and the phase shift coefficient, right? But I also want to discuss, yes, I have found my red pen. So let's just make a big circle here. That's 500 hertz on the left side. And over here on the right side, this is 500 megahertz. And I want you to look at that. Now, I did not put down what R sub S is in either of these because we've already gone through that in the last lecture, right? You understand all of, the difference between R sub S and C, and R prime and C prime and L prime, and that G prime is always 0. Now, I want to look at the difference. We're looking at the same wire here, the same coaxial wire. And this coaxial wire that we're looking at, and that's why I wanted to, use things that you guys are so familiar with, because you're so familiar with that coaxial wire behind your TV set, right? Maybe that's not how you watch TV anymore, but there used to be a coaxial cable, and you guys are all old enough. Maybe your children won't be, but you're old enough to remember that coaxial cable. You know what size it is. And here's the difference in attenuation. Here's the difference in attenuation. Let's get a black pen. Between two different waveforms. One that's 500 megahertz, that's minus 48.6 decibels per kilometer. And one that's 500 megahertz, that is minus 0.076 decibels per kilometer. Now, let's think about this. If I have a 500 hertz signal going through that coaxial cable that you have behind your TV set, right? Theoretically, if I had 1,000-kilometer long cable, right? No kinks in it, no nothing, no connections, just 1,000-kilometer long cable. That would only come up to 76 decibels, minus 76 decibels attenuation, right? That's not hard. You could easily put a detector at the other end that could look at a waveform that came in at, let's say, 1 volt peak to peak, and then had 76 decibel attenuation at the other end of it, and that would be 1,000 kilometers, right? Over here, how far could I go with a 500 megahertz signal? 500 megahertz. Now, that's usually what we put through a coaxial cable, right? Now, talk about the hierarchy of those in a little while. Let me just write that down so that I don't forget it. Hierarchy. Of course, I did forget to time this lecture, but that's fine. I have an idea. Just like, yep, okay, got it. No problem. So I'll keep an eye on that. I have an idea how long we've been going, and I sort of have an idea of the clock on my computer, so we should be all set. Now, this would go about 1.5 kilometers, wouldn't it? So I could go 1,000 kilometers and still get my 500 hertz signal through there, right? Or I could go 1.5 kilometers and get my 500 megahertz signal through there. Let's look at the phase shift. Let's look at the phase shift loss, energy loss. So this with a 500 hertz signal going 1,000 kilometers, I would only have 16 radians, right? Does everyone see that? 16 times 10 to the minus 3. So if I multiplied that by 1,000, that would get rid of this, and that would leave 16. So 16 radians for 1,000 kilometers. Whereas this one with a 500 megahertz, this is 16,000 radians per one. Well, that should say, wait, that should say kilometers. Yep. Oh, well, I just wrote it down wrong. Yep, that's good. There we go. So, no, and I wasn't supposed to put it there, was I? That's fine. That's why I've got this white marker. Okay. So, there we go. And I want you to really see the difference now between the two frequencies. And to drive that point home, I want to look at, in this lecture, I want to look at a larger coaxial cable. And in fact, you have seen this cable as well. Now, I'm going to keep the same characteristic impedance. The characteristic impedance is 75 ohms. And we want it to be 75 ohms so that if I connect up this big cable to one of the small cables, which is exactly what I'm doing, this is exactly the problem I'm showing. You know, if you look on a telephone pole on any street that's got cable running along it and cable drops going to the individual people's houses, right? You'll see that that cable is much larger. That's about an, you know, more like an inch in diameter. You know, a little bit over an inch in diameter, about 1.5 inches in diameter. You'll see that thing going down the street, right? And then you see cable, and then you see, you know, it comes up to a junction box. You see cable drops going off that junction box. Well, that is a trunk line, a 75 ohm trunk line for the cable company, right? Now, instead of its radii, if you look back and you remember what we had here, you know, A and B, the distance there and the distance there, and always remember that it's the radius, it's not the diameter that we're talking about, because that comes in handy. Always use the radius, and that's what I say. In all circumstances, use the radius, and then you never have to have any problems. Even if I give you the diameter, immediately turn it into a radius and use it that way, because I'm doing it as to trick you, aren't I? Because most of the time we just use the ratio of B over A, and the natural log of B over A. But in some circumstances, like R prime, where we're looking at the you know, ohms per meter, we don't, do we? We actually use the number. So it's not like you could put in the diameter there and it be equal to the radius, because we know the radius is 1/2 the diameter, so it wouldn't work out right, would it? That's right. So for this, we've got A equals 5 millimeters, and I'm going to talk about that in a second, because you're saying, oh my God, 5 millimeters, that's like a 1 centimeter diameter copper wire. 1 centimeter diameter copper wire. God, how much would that cost to put in a trunk line going to on the telephone poles? Isn't that what you're saying right now? You're saying, God, that's expensive. You know, I can see a solid wire in a little coaxial cable, you know, going to the back of my TV set, but I can't see a 1 centimeter diameter copper wire in the middle of this 75 ohm trunk line going down the street. You'd think that people would be ripping those things down and selling it for the copper. No, that's what you're thinking, isn't it? Well, I'm going to talk about that in a second. But what that also means is that B would be 6.8. What is it? What do I have again? 6 point. No. 6. Oh, I can't remember. But I do have it figured out, and that would be 34 millimeters. What was it? 6.82, 6 point. I can't remember. Anyway, I'm sure it's here, and I'll run across it in just a second. But that's not the point that I'm making. We're keeping the same B over A ratio, and we have to do that, don't we? Because we know that the characteristic impedance is eta, and again, I'll write down what eta is. Eta is always the square root of the permeability of the dielectric. I don't want to really put a D there because I'm just going to tell you it's the dielectric, and of course you know it is the dielectric, over epsilon of the dielectric. Notice I haven't put mu sub r and epsilon sub r, I've just put mu and epsilon, and the reason for that is, here, why don't I do that? Mu sub r, mu sub 0, epsilon sub r, epsilon sub 0, right? And for the dielectric. And of course, we already figured out what that is going to be, because anyway, let's go on with z sub 0. So divided by 2 pi. I've already gone through that, so I'll let you guys refer back to the last lecture in your notes, and then that times the natural log of b over a. So you can see the natural log of b over a is just going to remain the same. The ratio of b over a there is the same. Let me just give that to you. That is 6.8. I think it's 6.81, 6.82, something like that. All right, so the natural log of 6.82 is 1.92. And I'm not even going to put that in there because I'm just using this equation here. I'm just showing you that all of the equations for the larger trunk line, because the ratio of the outer ground shield, right, the outer ground shield to the inner core diameter, radius, is going to be the same, right? So we've got the same ratio. Now you're probably wondering, 1 centimeter diameter, piece of copper in the middle, right? That's crazy. So here's what I want to do. I want to show you. It's an AC waveform, and remember what I always say, AC waveforms dependent upon their frequency. AC waveforms dependent upon their frequency penetrate a perfect conductor down to the skin depth. And we did an example problem of this with submarine communication, old submarine communication. Now they use a blue-green laser and they do it at, gigabit speed. But old submarine communication used to be electromagnetic waves penetrating the conductive media that's seawater. And of course we did that. I'm sure you're familiar. Let's go through that. I want to write down 2 things here, really, because the way that I want you to remember this is the square root of the resistivity. I'm going to show you why I want you to remember that, of the resistivity over pi mu f, right? Now that's the surface penetration of the electric field into a conductor that has this resistivity. I want to set that aside from the other equation that we have. Let's just box out z sub 0. And the other equation that we have, which is r sub s. And I don't want you to get these equations confused because they're 2 totally different things for 2 totally different phenomena. And this is pi f rho. Oh, I should have done that mu. But you can see that when we're looking at r sub s, which is common to figuring out what the propagation constant is, right? You have to have r sub s to find out r prime. So r sub s is pi f mu rho. And this is rho divided by pi mu f. Does everyone, see the difference? It's not these three guys here. I'm going to use the red. I'm going for the red. These three guys here are on bottom, and these three guys here, why did I do that? Are in the top. Right? So just remember that. Write that down. Write it down a couple different times so you can remember the difference between the two. Now, I'm doing that on purpose because the center conductor in the trunk line is copper, right? So let's just do the math here for a second. So we know that copper's resistivity is 16 times 10 to the minus 9 ohm meters, right? And we know that pi is pi. And that mu is going to be 4 pi, which is 12.56, you can use that, times 10 to the minus 7 henries per meter, right? I'll extend that out a little bit. And then our frequency. Now in the trunk line, the cable trunk line, I'm running at cable speeds, 500 megahertz, right? So 500 times 10 to the 6 hertz. I could have wrote mega because, you guys, of course, would know that. And then at the end there, this is all taken to the square root, right? So I should just put something up there too, I guess. I don't know. It's all included, and it's taken to the square root. Now, this is the penetration that it goes into the outside of the copper, because let's not forget, AC waveforms travel on the outside, DC waveforms travel on the inside. Keep saying that over and over and over to yourself till you get it right. And how far, now we know, in regular 60 hertz power lines, the skin depth is actually thicker than the wire diameter. So really, the AC waveforms traveling throughout your house and traveling over the lines that we have, even the transmission lines are traveling their skin depth penetration is pretty much, it's like half an inch, more than an inch. Which doesn't penetrate the lines, actually, the high tension cable lines. They have an outside aluminum covering of almost pure aluminum electrical wire. And then on the inside, of course, is the cable, the steel cable. Anyway, I don't want to get back into that at all. I talked about that before. Let's get back to this and look at the penetration depth. And I think that all of you are already ahead of me. It's 2.85 microns. There you go. So you're probably saying, oh my God, there isn't a 1 centimeter diameter solid core in those trunk lines, is there? No, it's hollow. So they can save money because it never penetrates into the core, does it? It rides on the outside 3 microns of that trunk line. So we can, in fact, they make it a lot thicker than 2.85 micron wall, but you get the idea. So anyway, I thought that I would point that out. However, let's go back now and analyze this. Now that we know, how the design, how this then feeds into the design of the the trunk line coaxial cable. Now let's go and feed back into the things and see what we get. Well, we know that it's going to have the same ratio of A to B, right? So we know a couple things. And we know that this uses the same dielectric, right? So it's got the same dielectric in the trunk line as we have in the coaxial cable. And of course, by dielectric, I mean the foamed polyethylene that is inside the coaxial cable, right? That's the dielectric I'm talking about, the insulator, the dielectric. It's a dielectric. Most dielectrics are insulators, but not all dielectrics are insulators. I want to point that out. Let's go back to this then. So we've got the 2.5. Then we look at C prime. Since it's all the same and it's got the same dielectric inside, C prime has to be the same. So it's still going to be 68.3 picofarads per meter, right? And L prime, since L prime doesn't use frequency in its calculation at all, it's 384 times 10 to the minus 9 henries per meter, right? Same as it was for either of the two earlier examples that we did. R prime is going to change though. So R prime, right, is still going to use the same S prime because there's nothing in R sub S, I should say S. R prime is going to use the same R sub S as we already calculated before. And the R sub S from before was 5.63 times 10 to the minus 3 ohms. So let's just put that in there, 5.63 milliohms. That's R sub S, right? Over 2 pi. And then that is going to be multiplied by 1 over A, so 1 over 0.005 meters plus 1 over 0.034 meters, right? That's why we've got to use R here all the time rather than D, because this is not a ratio, is it? So that obviously forces us to do that. And we also get an R prime that's much lower. In fact, R prime for this is 0.246 ohms per meter. So it's 1/4 of what it was, less than 1/4 of what it was, because if you remember for these two, we had R prime being 1.03 ohms per meter. Right? Oh, wait. No, I don't, wait a second. No. One was 1.03 ohms per meter, and what was the other one? The 500 megahertz was 1.03 ohms per meter, and the other one was 1.03 milliohms. The 500 hertz was 1.03 milliohms, but we're really comparing these, aren't we? We're comparing the smaller cable now to the larger cable. We're comparing the cable that had a 1 millimeter inner signal line diameter, that's the one behind your TV in your house, to the one that's up on the telephone line now. So let's not even think about the 500 hertz right now. That could only add to the confusion. In between these two, we were changing the frequency and seeing how that affected the attenuation rate and the phase shift constant, right? Let's just draw a line around that. But here, what we're doing is we're comparing both at 500 megahertz, keeping the frequency the same, but now changing the inner diameter from 1 millimeter to 5 millimeters. And you can see that that reduced this by about 4, a factor of 4. So increasing by 5, decreases by 4. Now how does that work out for the propagation constant? I know, so let's just look at this for a second. Well, we know that it's the square root of R plus J omega L, right? So R now is going to be 0.246 ohms per meter plus J omega L. Well, that's still going to be the 1205 ohms per meter that we calculated earlier, right? Because nothing's changed. L is exactly the same. R plus J omega. Omega has stayed the same, 500 megahertz, so that makes omega 3.14159 times 10 to the 6 radians per second, as you know. And so, so that's what we've got. So we've got that. That is the same as it was before. And then let's multiply that. Now we know G. So this times G plus J omega C. I probably should write that out someplace down here. Gamma equals the square root of R plus J omega L. Everybody has this anyway. Times G plus J omega C. Well, that wasn't too good. C prime, G prime, L prime, R prime. All right, so we've got those, and then we're going to multiply this, and we know that G is always going to be 0 moles per meter, right? Plus J omega C. Well, C didn't change at all. Omega hasn't changed at all. So why would anything else change? So that'd be 0.2136 moles per meter, and all of that taken to the square root, right? So that's what I've got for this larger trunk line example that we're doing with the coaxial cable, the 75 ohm coaxial cable. Yep, you'll know everything about Comcast by the time you're done with this. Now let's go back and see how that all works out then. Well, if we do look at that, what we end up getting is we end up getting the square root of minus 257 plus J 52.5 times 10 to the minus 3. And you can see that that's a much lower number in the J part there than we had before, right? And of course, that's taken to the square root. And when we take this number to the square root, we can change it into its phasor form. I'm going to do that for you. That would be 257 at an angle of 89.994. Oh, wait, no. Wait, no. Yeah, well, that's wrong. Just a second, I'll give you the angle. Just a second. 89.994 times 2, 179.988. Where is my, there it is. So, good, because this is when I took the square root. So I'm one step ahead on my angle than I am. I think I've run out. No problem, I've got another one right here. And that should take care of the bottom part there. All right, so it is 179.988. And that's going to be taken to the square root. And this is where the other one comes in. So this is 16.03 at an angle of 89.994. Now, I know you think that these are so close to 90, so close to 180. Why don't I just round those off? No, I don't want to do that. And the reason for that is that if you would round them off, then you would have the attenuation constant be 0. Whereas at this rate, what we've got here, let's write this down. And I'm going to circle this in red too, because when I break this back down into a complex number, a plus jb rectilinear form of the complex number, I get, I'll write it out like this, 0.00164 nepers per meter, right? That's my attenuation coefficient, plus J is just a marker, 16.03, and I don't want to take that out any further, radians per meter. So if you look at it, the 16 radians per meter here and the 16 radians per meter here, irrespective of the size change, is the same, isn't it? All right. Just so that you can see that. How about over here, though, this 0.00164 nepers per meter? Now, what does that turn into? It, well, I'm going to turn it into this. So if we got that, let's just say that alpha, let's just write out alpha. We know beta. I'm going to put equals beta down here, right? So I don't even have to worry. Everybody knows that's beta. We're not going to change it. Get radians for, 16,000. If you want to do that per kilometer, that's fine. But let's do this. This would be, if we looked at it per kilometer, it would be 1.64 nepers per kilometer, right? 1.64 nepers per kilometer. Let's compare the kilometer attenuation. Now, this is the cable behind your house, right? Or behind your TV set. This one gets minus 48.6 decibels per kilometer. Well, if I go out to the trunk line, though, that's in front of your house on the telephone pole, I end up getting minus 14.2 decibels per kilometer. Do you see the difference? Do you see why we use the larger ones? We don't really use much more copper in larger ones than we do in the smaller ones. Do you see why we use the larger diameter ones on the trunk lines where we can get 1/4, right? Look at that. That's 48. Let's see, 14 times 4. That'd be 4. Yeah, it's about 1/4 of the attenuation for those trunk lines that you would get using the same kind behind your house, right? So they use those as broadcast trunk lines, and then of course they come off there with feeder lines to each and everybody's house. All right, I've run out of room on the page. I have no real idea how long I've been talking, but I'll find out in a second. And I'll talk about this hierarchy of communication bandwidth over metallic conductors next time we get together. Let me just write that down somewhere. Hierarchy of, I don't even know. I'll have to write it on the, I'll write it down here, hierarchy. I'll go, why did I write that down there for the next lecture? All right, it's a reminder. Thank you so much, and I don't know if I'll get another lecture done today. There's, like I say, there's a lot of things going on. I'm certainly not shoveling gravel. Okay.